looking at this, what I mean is that when you go and pitch, so here is our pitching, you'll see, bam, we already are getting ready to hit right there. I mean, it's very, very, very close. And my pitch is like 35 back that way. And then I'm going to come on up to here, and you can't get much more at this point, you actually are running out of length here. There's only so far you can move that. And the other thing you got to be careful of is that as you're pitching this, you see how this is moving forward. If I pitch that anymore, that actuator is going to move forward and is going to hit the front of the shin. So that won't be a problem. So now what we need to think is like, oh, okay, let's go ahead and put some actuators in here. So in the case of Tesla, the actuators they decided to put in are linear drives, or what are prismatic. All right. So these are prismatic drives. You may have noticed down here, these two little balls, which look like spheres. I don't think these are the spheres they're referring to, though they could be, because there's also some spheres right up here that you may have noticed, and that these are very important for the system to work. So there's your spherical, prismatic, universal. That's where the naming of that comes from. Okay, now, in order to move these things, what you need to do is come up with a desired orientation of your foot. So for instance, I would like my foot to be at that attitude. Okay. And now I need to calculate what my motors have to do to get my end effector, which is my foot, in the position it needs to be. Well, classically, that's called inverse kinematics. So like, this is a desired position. So now I need to know what my joint values need to be to get there. That's an inverse kinematic kind of problem. The opposite one is like, oh, imagine I move these joints to some position. Where is my foot going to end up? So you can see why Tesla sculpted everything out, is they had certain limits they had to play with, and they had to go in and make sure everything doesn't bump into it. And you also have like this forward movement back and forth of the upper joints to make sure there's enough room in there. So that's one of the things you have to consider when you do your analysis, to make sure that the actuators actually fit, because they're going to be moving around. So that's an example of the SPU kind of connect. Well, not exactly. And as you can see, it's the same old problem that as I move this, you see, what's going on here to get the crank to kind of fit in there as it moves around instead of missing everything. And I need to solve that. And so this is where forward kinematics becomes difficult, that when I move this and move that, it's kind of tricky to figure out, oh, okay, what do I actually want to do here? So I guess I want to move that there. And then, do I then move this? It's like, it's really tricky. And it could be that that's a prohibited position. You can't do that. It's not reachable in the space. So that's the other thing, is you put in these combinations that maybe that it absolutely doesn't make sense. Hi, Marwa. Good afternoon.
Hi, Scott.
Yeah, so today's topic is going to be a little bit different. There was a paper that I saw posted on X. It's rather interesting, talking about robot ankles. And we haven't really discussed the ankles yet. And we're going to go into this paper a little bit. Believe me, I think it will be worth it if you're interested in understanding different ways of doing actuation strategies for ankles. And so it was a paper that was put together for the Coral conference that's going on in Korea right now. And so I'll go ahead and share this paper so we can get an idea. And maybe this will help anyone that does see the paper to sort of understand a little bit about what's going on in the topic. So the title is A Framework for Optimal Ankle Design of Humanoid Robots. And this is by Cervetini et al. Out of the Italian Institute of Technology. I think in Genoa, but they've got campuses all over the place, so it could be somewhere else. And what they're doing is they're kind of classifying some of the robot ankles and doing an analysis to figure out which is sort of the ideal or the best one for maybe certain applications or just overall. And part of what I liked about this is that when you read the abstract, it's for the first time that someone has given a name to these ankles. I've asked a lot of people, it's like, what do you call this actuation strategy? And they're like, oh, it's like a parallel kinematic, or it's a MIMO or something like that. So they actually talk about two different architectures: spherical, prismatic, universal, or SPU. And the other is revolute, spherical universal, or RSU. It's a bit of a mouthful. We'll understand exactly what they mean by that. It's typical robotic speech, I guess you can say, or speak. And what they're doing is they're kind of comparing different ways of actuating an ankle. So over here on the left, it's not like the best representation of it, but it's a serial um, type of ankle. And that's like, that would be, say, the standard or classical approach to trying to create an ankle, is, say, in some ways the easiest. And then two different parallel actuation strategies. And the first one here in the middle is the SPU. That's the spherical prismatic universal. And this is how Optimus, how Apollo, how Iron, how Neura, how Kepler, how they all do their actuation of the ankle. So they're actually using what is a linear mechanism to do it. That's basically what prismatic means. It's, like I say, it's the roboticist way of saying, oh, a linear drive. They mean prismatic. And then over here, we have what is the Revolute spherical universal. And this is perhaps the most common ankle actuation strategy you see out there. Just about every Chinese robot, like Unitree or Fourier, use this, as well as Boston Dynamics, Agility. They're all using this kind of mechanism. But we haven't really been able to see how the trick is done, because usually it's behind some sort of covers. But so today we'll get a chance to get an idea of exactly what that looks like. Okay. Any questions so far?
No?
All right. So moving ahead here, they do talk about, the advantages of parallel mechanisms. So there are definitely inherent advantages over serial actuators. Part of it is like the rigidity, the precision, basically the averaging of chain errors, which I guess maybe that will actually help precision, though it may add more. But I think one of the biggest advantages is this idea of torque sharing. The fact that you can have two actuators actually help you move in a particular direction with twice the torque that you normally would have. And also, like, this idea of improved dynamics from the relocation of heavier components to proximal frames. What does that mean? Well, if all of your mass is out at the very end of your robot arm, it's much harder for it to manipulate it than if you move it in towards the center. So the idea is, by lifting up higher, closer to the top of the leg, that means the leg's able to walk faster and expend less energy, basically, because the overall moment of inertia of the entire chain is less. Um, However, it does come with some downsides, and that is, you need to account for the fact that the torque joints are going to vary over the workspace and the velocities. And it's a little bit harder to capture mathematically, so that might make, training a little bit more difficult. Whereas, the serial mechanisms, the performance metrics, are basically specific to that joint. So, parallel requires an architecture that require a global coupled optimization. You just can't optimize in one particular joint. So, and the other thing I liked about it is that buried in the text, they talked about, the fact that this architecture gives enhanced compliance, improves both robustness to unexpected terrain asperities. And
This is a new word
it's
you
a
learned.
new word for me. And it basically means like harshness or things that are kind of unexpected or rough. So you could just say terrain roughness. So it's probably an archaic word. I think it's a very common word in Latin. I think it comes from Latin. And since the authors are Italian, they probably have that word in Italian and say, what's it in English? So great. I learned a new English word. It's yeah, it's actually out there. So yes, asperities. Okay. Now, another idea that they kind of introduced, which will be important, is this idea of a manipulability ellipsoid. And what that means is that ideally, wherever you are in your workspace, you would like to have the same amount of performance regardless of the direction you're moving in. If you're going to go forward, left, right, up, or down, or if you're going to rotate one direction or another. And usually in your neutral position, you have that. But once you get to other configurations, you sometimes two actuators will reinforce capability in one while they're losing it somewhere else. It's basically, are all your actuators rowing in the same direction or not? And what that means, if you were to map it out, and this is basically using the Jacobian matrix to figure this stuff out, and eigenvalues and eigenvectors, which some of you may or may not understand. But it's a way of saying, how much manipulation ability do I have going forward versus left and right? And whichever I have the best capability versus the least capability, I'm going to make a ratio out of it. So this is one of the parameters they're going to kind of be measuring and looking at these configurations. And I just kind of bring it up for that reason, because it's an interesting concept of this idea of an ellipsoid kind of at the end of your end of arm tooling that shows the capabilities. And actually, when you get to the singularity, that ellipsoid collapses down to like a pancake. It gets like there's one direction you actually cannot move at the instant of the singularity. Okay, so um, at some point in here, they go through some pretty dense text with a lot of Greek letters in there, where they talk about the inverse kinematics of the mechanism and what that is. And I'm going to try to break that down, make it a lot easier for everyone to understand what's going on. So, the first thing is that you can sort of look at a graph that would describe how this parallel mechanism goes together. And typically, when we think of a serial link mechanism, we talk about forward kinematics and inverse kinematics. And for a serial mechanism, forward kinematics is really easy to do. The inverse requires a little bit of math. For a parallel mechanism, it turns out that ironically, the inverse kinematics is actually fairly simple. Still requires a little bit of math to figure it out, but the forward kinematics is like almost impossible analytically. You need to usually do iteration and everything else. It's really a mathematical challenge, believe it or not, to do the forward. And I'll explain what I mean by the forward kinematics in just a second versus the inverse. So they show a couple of diagrams here of the setup of how they want to model everything, SPU versus an RSU, where they talk about the mechanism having a shin, a foot, a slider, and a linear guide for the prismatic version. And then the RSU having also a shin and a foot and a crank and a rod. And we'll see exactly what that is. Now, this may be a little bit hard to understand at first, kind of looking at the diagrams and understanding what all the letters and everything mean. So what we're going to do is we're going to go to a really simple example right now. So I'm going to jump in and we're going to build up both these different types of arms using a real world example, the Optimus bot and also the AGI bot, where I was able to get some CAD data to represent those. So what I need to do first, I'm going to jump into another screen. But before I do that, any questions at this point?
No, I'm very interested. How did you get the CAD model from? That's first
I,
question.
I I know some people.
Okay.
Who
Okay.
know some other people, and eventually they end up in my inbox. Well, actually, the AGI, I think that might be available through Mujoko or something like that. There's some open source areas to that, and I suspect the Optimus one was a bunch of people doing some reverse engineering of the Optimus model in public using like their smartphones to go around and do a 3D scan, and so that's most likely what it was. Okay, so I think I'm still sharing the wrong screen here. So, fooled myself. And what I want is this one here. Okay. Yes. So this is the image that we're going to have. All right. So we have both different ankles here, and I'm going to start with the Optimus ankle. So I'm going to go ahead and make the AGI bot over here. So, I mean, we can kind of zoom this around a little bit just to sort of, see what we have. And so the AGI, I will just go ahead and make that invisible right now. And so here's the Optimus ankle. And pretty much what I'm going to do is, um, like I say, build everything up from scratch. So I'm going to make everything disappear. All right. So the first thing they talk about this is an SPU. So it's serial, prismatic, universal. Let's start at the end. We're going to start with the universal. This is a universal joint. Okay. This is the universal joint that we actually see in Optimus. And I'm going to try to zoom in here a little bit better. Okay. And a universal joint is usually just two axes that cross one another. It's also referred to as a Cardan joint at times. And in this case, you'll see there's an offset between the two axles. Now, it may not be obvious how the universal joint works. So what we're going to do is we're going to bring in the shin. So the shin is basically the fixed frame that everything is built on top of. So the shin will not move, but the foot's going to move with respect to the shin. And once we have this, you see this is able to rotate about that axis. And that's what we refer to as the foot pitch axis. So that's pitching right there. Now you can see this other axis right along here where we can say, oh, okay, let's go ahead and throw a foot in along there. So now we have the foot, and I can now take the foot and not only pitch it up and down, But if I want, I can now rotate it back and forth this way. So that is what they call the foot roll. So we have pitch and we have roll about those two different axes. And that's basically how a universal joint works. Like I say, most universal joints will not have this offset. It's up there. Tesla probably decided to put in there, I think, for access and collision avoidance. I mean, there's no real challenge to having to deal with that offset. It doesn't make the math really that much harder. So that is how the universal joint works. The question is, how would you actuate that? So any ideas if you were building something like this from scratch,
Mm.
one possible way is like right up here, in that pitch axis, why not just build like a big actuator right there? Like we see at the knee and the elbow and everywhere else. Let's just go ahead and see if we can fit an actuator in there and it will go ahead and create that axis for us. And we could do the same thing down here. We could probably build something at the top of the foot. And that means both of them are actuated by direct drive rotary actuators. And that's your serial linkage. There are very few examples out there that actually do it. Figure I know does for sure. There may be a couple others, but almost no one else does a serial ankle. Everyone else is using one of these two versions, SPU or RSU. Okay, so that means if I want to actuate this, what's one way of doing it? Well, I mean, just imagine, for example, for a second, we go ahead and put something back here. It's going to act like a handle. Okay. So if I kind of grab this handle, it gives me a moment arm here where it's really easy for me to move this thing up and down. And then you can imagine if for some reason I push on one side of that handle a little bit harder than the other, I can get it to move around that way. So this is sort of the idea of what they're trying to do with this parallel actuation is if I can push down on different sides, either together or in a differential mode, I can actuate these different axes along whichever direction I desire. So that won't be a problem. So now what we need to think is like, oh, okay, let's go ahead and put some actuators in here. So in the case of Tesla, the actuators they decided to put in are linear drives or what are prismatic. All right. So these are prismatic drives. You may have noticed down here these two little balls, which look like spheres. I don't think these are the spheres they're referring to, though they could be, because there's also some spheres right up here that you may have noticed, and that these are very important for the system to work. So there's your spherical, prismatic, universal. That's where the naming of that comes from. Okay, now, in order to move these things, what you need to do is come up with a desired orientation of your foot. So for instance, I would like my foot to be at that attitude. Okay. And now I need to calculate what my motors have to do to get my end effector, which is my foot, in the position that needs to be. Well, classically, that's called inverse kinematics. So like this is a desired position. So now I need to know what my joint values need to be to get there. That's an inverse kinematic kind of problem. The opposite one is like, oh, imagine I move these joints to some position. Where is my foot going to end up? That's the forward kinematics. And that's the one that mathematically is tough. Fortunately, we don't actually have to solve that because usually what's happening is that when you're walking or doing something, you know what you want the angle. In other words, the universal joint. What do I want those angles to be at? And now that I know what that is, please figure out what the displacement along the motor has to be in order to be able to do that. Now, if you look at this right now, you'll see that the system is broken. I actually haven't connected everything together here because I have to figure that out. I have to make some sort of calculation on that. Well, one way I could do that is I could just kind of move it over and eyeball where that thing has to go. It's like, if I get it right about there, I think that's about right. And then if I move it up like this, you'll see, oh, what I need to do is I need to make that down a little bit longer. Oh, but wait a minute, I probably have to also move this a little bit that way as well. And so there's a lot of that movement that kind of goes along to figure this out in order to get it. And that's really key and quite critical to what's going on. So the first thing I'm going to do is explain how we're able to calculate that, but motivate that. So the first way to motivate it is that I've got two ways of solving stuff here. The first thing I'm going to do is I'm going to solve what is the prismatic problem, solve P. So you see that I got the length right, but I don't necessarily have this right. So on the other side, the length is correct there. And if actually we come from behind and we start doing something like, oh, let's change it in the yawing position here, you'll see you get that differential movement that's going on there. So both sides are different, but you see, but you haven't been able to line these things up right where they're supposed to be. So that means I have to solve this problem of figuring out what you have to do to get it there. And you may look at that and go, oh, looks like you got it solved. And you come over here and realize, oh, wait a minute, it's off just a little bit there, isn't it? And I can take, so there's actually two angles you have to solve for, not one. Now, from the standpoint of having a mechanism where I need to know how long and you need to make that, I don't care what the angle is that I need up there because the system will self-balance. The forces will all balance out and it will take care of itself. The only reason I need to then solve this next step here is because I want my simulation model to look correct. And would really look stupid to not, to that as I move it around to see that, oh, that goes up and down, but I don't see the connection. So what I'd like to do is solve the whole problem. And so when I solve the whole problem, you'll see everything starts moving around up at the top and you'll understand why this is a spherical joint. So if I kind of go back and get ourselves to a nice kind of front view here, as this goes up and down, you can see very clearly there has to be some rotation happening down around here on that joint. So that's why there is a ball there. It could be done with a pin. You think, why not just use a pin joint there? And you could potentially do it up there. And you'll see there's still a little bit of wobbling up there. And if you don't do that, the system will bind. But the real reason you need to do it is that when we go, let's say up to the backside over here, we'll begin to see that when I move this back and forth, you'll see it also wobbles a little bit up there in the other direction. So that means I need to have both degrees of freedom. And that's what a ball joint or what's known as a Heim joint is able to do for you and do them in both places. The other thing I want you to notice is that how extreme the problem is down here. I'm kind of limited to how much I can roll my foot, partly because this Heim joint's going to break. It doesn't really like move, even though it's designed to move in two directions. It doesn't like moving in that direction. It prefers along that axis. It can rotate all day along that axis without a problem. The other problem we have here is you can see, wow, wait a minute, this could potentially impact the actual bone structure here of the shin. So you can see why Tesla sculpted everything out is they had certain limits they had to play with, and they had to go in and make sure everything doesn't bump into it. And you also have like this forward movement back and forth of the upper joints to make sure there's enough room in there. So that's one of the things you have to consider when you do your analysis to make sure that the actuators actually fit because they're going to be moving around. So that's an example of the SPU. And now what we're going to do is we're going to have some fun and actually go in and see what the math is like. It's not that bad. Hang in there with me. I'm giving everyone a break of a little bit of a animation here along with some slides. So right now, what I will do is go back to those slides.
I have to say
Yeah,
something. The
go ahead.
animation
Mhm.
much easier than the paper. Just the paper, to be honest, is
Yeah.
very
Like I say,
troublesome.
the
I,
paper,
I, it's,
the paper's a bit dense because all the Greek characters everyone has to throw in there. Because whenever you're an academic, you have to throw around words like revolute and prismatic. What does that mean? It means rotational and translational, but that's the term of art. And that's what you have to do when you go to conferences if you want to sound smart. And then you, rather than using like letters A, B, and C, you have to use alphas and betas and gammas and all these other things and these weird scripts and subscripts and everything like that. Because it make sure that everyone knows, oh, you're an academic. But what I want to try to do is make sure people understand it, because the biggest problem I found is that every time I tried coding this stuff up on a keyboard, it's like, you know what? I don't know any computer language that accepts Greek letters. Everything is going to be Latin and that's it. So, I'd always have to come up with something else to kind of fit in there. And so sometimes it does become a bit obtuse when you start seeing terminology like that. Okay. So going back to here, I think I'm sharing right now. Yes. Um, let's take a look at the coordinate system. So again, we see the optimum spot here where I'm only showing the shin and I'm showing the foot and the universal joint down there. And you can see down the bottom where these balls are for the Heim joints. And the trick to solving this problem is we need to think about a couple of coordinate systems here. So right here at the ankle, this is the world coordinate system. This does not move. And the shin doesn't move either, except up here is connected to the knee, so obviously it's rotating there. But for all intents and purposes, this shin is rigid to the world frame of reference, which is defined by here. And up here, we have the spherical joint in the SPU. So that's the sphere they're talking about that I've labeled as P1. And that's always a fixed offset from here to there. And then we also have this point here, P2, which is also, it's going to be a moving frame. So we have to sort of figure out where it is with respect to the world as we go along. Now, what I want to do is I want to calculate these three vectors. So this blue vector, which is a distance basically from here up there, but it's basically a vector because it has a position in space with respect to the world frame. And then I want to calculate this purple one, but this purple one changes in length. That basically is what is going to tell me how much I need to actuate this whole thing, dependent upon how much the foot moves around. And there's going to be this little orange frame down here that I'm going to need to calculate. And so the first thing is like this blue frame here, that just comes out of the engineering drawings. You measure it once and that's it. You know, it's just it's given, just some numbers that are there. So you don't have to worry about that. Now, the next thing I want to do is I'm going to kind of zoom in here a little bit closer and start labeling this a little bit better. So I do that so everyone doesn't get lost. So what's happening down here at the ankle is you have the very first rotation of the universal joint is this green. That's the foot pitch. And then after that pitches, it results in this whole structure moving, which means there's now an offset that goes here in the blue down to the center here. And then you have this rotation in the red, which is the roll. Okay. And then from here to there, this white vector, that vector is fixed. That's also given. So the distance from here to there in that particular part space is always fixed, it's given. What we have to calculate is this dashed one. That's the thing that's always changing. And that's going to be the position of this point in the world frame, which is the same world frame that the shin has for P1. So they're all in the same frame of reference. So what happens is that when you begin to, what you want to do is basically say that this orange vector is basically equal to this order of operations. The green rotation plus a translation in the local Z of the new frame, then that rotation plus that. So add all these things together and you will get that. Okay, that's the order of operations. Basically, it means this is what you do, is that you calculate the rotation, you create a rotation matrix about Y of pitch, then you translate in the local Z by whatever that Z offset is, then you rotate about X about this roll, and then you concatenate that with this W vector, and that gives you the P vector. That's the order of operations that you go through. So what ends up happening, of course, is that if you pitch this thing around, you kind of see, okay, we rotated it this way. That blue vector is now not in the world Z, but it's in the local Z. So it's still like a local translation down to there. You do all this stuff, and now that's the new location for P. Now that I know where P actually is, so pretty much what that means is like, take these two numbers. This is a fixed number, that's fixed. Plug that into this equation. You now know where P2 is. And as a result of that, all you have to do is figure out what this purple vector is. And if you kind of look at that, basically the purple vector is the orange vector, which we just calculated, P2, minus the blue vector, which is a constant that's given. So all you have to do is like, oh, that's what the equation looks like, which basically says, oh, if we call that thing L is just P2 minus P1. It's as simple as that. And that means if you take the magnitude of a vector, and remember the magnitude of the vector is just the Cartesian distance. It's the sum, it's a square root of the sum of the squares of each component. So x squared plus y squared plus z squared, take the square root of that, and that's the distance. And that tells you how much you need to offset it. That's it. So that's how you solve the forward kinematic problem. Now, as we've seen, there is a problem of like, well, what's the angle that goes in there? And that's a little bit more because it's a 3D reasoning problem. It's a little bit in there. But I think once everyone gets this far, once you know P1 and P2, you have all the information you need to solve the rest of the problem. Okay. So any questions on that?
No, I think it's I think this to be honest, the CAD model make it much easier, to be honest, to understand.
Yes.
And I appreciate that. To be honest, I'm fascinated because, first of all, just the leg, I didn't know, to be honest, that the rotary prismatic and then the
Yep.
universal,
Yep.
this
Yep.
configuration.
Yep.
So
Yeah.
it was
Oh, and
really nice. Yeah.
yeah, and one thing I forgot to show here is like, where all the different coordinate systems are that we can sort of understand what's going on. And, sometimes if I actually, I want to change this to a different rendering mode because sometimes the fancy rendering is not as sharp as everything else. So that makes it a little bit easier from the standpoint
I'm
of
afraid,
looking at it as an engineer.
I think we will ask for the STL file. Oh,
Loss of,
maybe
mhm.
they will ask for the STL file.
Oh, yeah, 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 yeah. So, possibly. And so you can see everything that's here, and where the frames and all that, and you'll see how I had to then calculate a little bit up there to be able to get that all fixed. Now, let's go ahead and bring up the other mechanism right here. So this is the example of the AGBot, and there's many different ways of building it. As a matter of fact, the mechanism that they show in the paper, it's organized a little bit different. There's a lot of different ways. Usually everyone has it about 90 degrees in this direction. So this is like sort of an interesting way of building a mechanism. But again, we're going to go through the whole exercise. We won't go through the inverse kinematics and stuff like that. It's actually a little bit trickier with this kind of mechanism than uh, the Tesla foot, but we can go ahead and take care of that. And okay, good. So we have absolutely nothing there. And we're going to start with the U joint again. So here is the universal joint. And we can sort of see that. Now, this is your more classic universal joint. You see, the two axes actually intersect. That's usually how a universal joint looks like. And we're going to build a shin around this thing. So we'll go ahead, bring in the shin. And now that we have that, and let me go ahead and center everything so things behave a little bit better for me. So now that we have that there, I can go ahead and take this and then rotate it around there. And once again, you could imagine, hey, I could probably build a motor right in there to do that, right? Sure enough. Okay, if you want to, you could go ahead and do that. And then we're going to go ahead and show the foot. So we now can throw the foot on there. And again, the foot's able to go up and down like that, but we also have this movement side to side, back and forth this way. All right. And once again, we're going to want to throw some sort of Heim joint in here. So that's going to be the joint that comes up that actually allows us to do the actuation of this just by grabbing the Heim joints. We'll be able to move it this way or that way, however we desire. And now we want to have some actuators. So let's go ahead and throw in the actuators. So here's our motors. And this is basically forming the crank. So we have the shin, we have the U joint down here, and we have the crank. And these cranks are basically, they can rotate back and forth like this, up and down like that. But you see the problem with that crank is it's not connected to anything. So without it being connected to something, the foot's not going to be able to go. So we need to go ahead and throw the links in. So we'll go ahead and we'll throw a couple links in. So there we go. We got our links, and hopefully we've got the distances just right that they kind of connect. Well, not exactly. And as you can see, it's the same old problem that as I move this, you see, what's going on here to get the crank to kind of fit in there as it moves around instead of missing everything. And I need to solve that. And so this is where forward kinematics becomes difficult. That when I move this and move that, it's kind of tricky to figure out, oh, okay, what do I actually want to do here? So I guess I want to move that there. And then do I then move this? It's like, it's really tricky. And it could be that that's a prohibited position. You can't do that. It's not reachable in the space. So that's the other thing is you put in these combinations that maybe that it absolutely doesn't make sense. So we've got, again, want to go to the forward kinematics. So if we kind of reset everything here, I need this thing to get in there, and you'll notice, oh, I've got this big problem that I might have to adjust it like this and get it down to get everything to kind of fit. So it becomes a bit of a technical challenge to eyeball and get everything. So what I want to do, of course, is I want to do a solver for it. So the first thing we're going to do is we're going to solve the R problem. So remember, this is an RSU. So revolutes here, there's the sphere, the spherical universal. In this case, it's more or less like sphere, and really, I think the first one should have been spherical, prismatic, spherical, universal, because that's really what's going on. Um, but in this case, it's basically revolute, spherical, spherical, universal. Okay, so they kind of shortened it. So let's go ahead and solve the revolute problem there. So that is basically the correct distances that we need, or I should say displacements that we need to have the uh, the actuators, the revolute actuators actually do in order to be able to get the foot in that position. What we now have to also solve is like, well, what's the angle that these things have to make on that spherical joint in order to connect up down there? And that's when we solve the next problem and they kind of come on in there. And then you have that. Now, the thing I want you to notice is that um, there are some deadlocks in here. Right now, you'll see the math kind of breaks down that as I move too far one way or the other, I'm getting this thing all the way to top dead center, and it really can't go beyond that. And if I'm requesting it to go beyond there, you'll kind of see that sometimes the mechanism breaks. So in other words, you would never really be able to get there, or it's going to bind up. There's just no way you could get there. So with this kind of approach, and it also depends upon how you put these two mechanisms together, because I think you'll see we are getting these things that kind of, self intersect with each other. You'd want to design them a little bit different so the two cranks don't bump into each other. And but you also have like limited movement of how much you can move your foot around. So everyone assumes you have like huge degrees of freedom here, but actually the degrees of freedom are far more restricted than you would believe based on all these self intersections and everything else that's going on. However, the range of motion that you have is about comparable to a human foot. It's not a lot more, and that's probably all you need. You don't need to be that much more than a human being. So you don't need to have, say, plus or minus 90 in the roll. So it's limited to maybe plus or minus 25, believe it or not. It's not, not a whole lot in the roll, but try doing it with your foot. If you're able to get 90, you're either very flexible or you just sprained your ankle. So it's one of those two. So that's pretty much how these mechanisms work. Anything else that you'd like to see on this one or even on Optimus?
I'm just
Oh,
thinking about
sorry,
one is the different design choices in the configuration. So they have the crank and then the prismatic and then the
yeah,
universal joint and
yeah,
high
yeah.
joint.
So that
And I was
yeah.
just yeah.
So that brings up a really good question. It's like, oh well, what should I use? Which is the best of the two? And this is the first time we've seen someone even attempt to do the analysis to argue for one over the other. And the in the end, their conclusion is that the RSU is better than the SPU. In other words, the Revolut is better. Um, though I think we had to take it with a grain of salt because even though they're trying to parameterize it, they're more or less showing a method on how you would go ahead to make this decision. And based on some assumptions that they had, they came to the conclusion that this is kind of better. That doesn't necessarily mean that's the reason why we see more of these out here than we see these, but we still see quite a few of these. A lot of times the design choice would be, I just don't like linear drives. There's just something about them. I don't know how to source them or something like that. The Revolut are a lot cheaper. So how do I do it? So you do it that way. However, from a mechanical standpoint, everything else, I actually think the prismatic approach, sorry, linear, is in some ways a bit more elegant than doing this way, even though they come to a different conclusion. And I'm gonna kind of go in there why I think I would argue against the conclusion that they had, or let's say be a little bit more open-minded. So yeah, there we go. We can always come back to this if there's more questions.
So you think the linear actuation in Tesla is an elegant solution?
Yeah, and you see, a lot of people would agree with that as well because they're not the only ones that do that. So their hip design, no one else is doing that hip design the way that they are. There's no doubt about that. So, but when it comes to the way they've done the ankle mechanism, they're in good company. There's quite a few other companies that are doing, basically Uptronic with Apollo is doing it. Xpeng is doing it. You also have Neura has taken that approach. I'm trying to think if there's any others out there, but I think there might be a couple that I think like maybe I don't know if Walker is doing it or UB Tech, but I think I've seen a few. So it's kind of split around there because there can be advantages and disadvantages. And again, that's why I want to go back to the notes that I put up here and discuss that a little bit more. So first of all, why does it matter to get the simulation of that right? So, you may remember in the past, I kind of criticized the fact that Tesla was showing the simulation, and you'll see how it comes apart up at the wrist. So basically, this wrist mechanism is the same as what they have down at the ankle, and they didn't even bother to show the displacement, which is a little bit disappointing. What's a little bit harder is getting the actual movement around the spherical part of the joint to get them to line up. And you need to be able to solve that to understand the range of motion issues. Because as I was showing, is that they could very quickly intersect different things. So you can see how they came up with that design. So they moved it around the workspace and they created pretty much a Boolean of the movements of everything. So they or swept volume of all of the actuators, and then designed around that swept volume and said, okay, this is where we can actually build everything. But there's other issues you have to figure out, like, well, what's the distances? How long should this thing be? What should all my different offsets? So you want to test that out. And that's what they do in the paper is in the paper, they parameterize everything. So you can try to make these kinds of decisions. And of course, they go through and they look at a lot of the different design spaces and everything else. And if you've looked at the Tesla AI2 day presentation, they had some images and stuff like that that kind of look like that. That looking at your design fronts and figuring out what is it you're trying to optimize. And a couple of things that kind of stood out to me, which is why I say you have to be kind of careful, is they were looking at some specific actuators to use. So they're using a Wittenstein linear actuator that is a ball screw. Okay. This is not a planetary roller screw. It's a different actuation strategy. So it may have different performance characteristics. So this is an apples to oranges when you want to compare it to Tesla, even though it's an SPU. And the other thing is that for the rotary actuators, they're using a planetary gearbox when a lot of other people are using harmonic drives. Not all. I think my understanding is that Unitree might actually be using a planetary gearbox, but a lot of others are using either cycloidals or harmonics. So you've really got to think about that as well. So they're really comparing these two and coming to certain conclusions as a result. And what that means is they come up with this kind of the spider diagram here where the blue one is the SPU, or the one which is using linear drives. And then the purple is using the Revolut. And when you look at that, you can say, well, yeah, it seems to score better in more places than the blue. And so we can kind of go around a little bit of this. So let's start at the manipulability ratio. This is showing that you have about equal capability to pitch and roll the foot, which is really, pretty good. It's a little bit better for the linear drive than that. And I can believe that because of when that the crank moves around, you're getting lots of weird angles in there. That means it's probably going to have a little bit of reduction or loss as you go in there. And you'll see the width of these things, the shaded area, that kind of shows that throughout the work envelope, how it changes, and really where they draw the line is kind of the average overall. Because again, like I said, the manipulability ratio is going to depend upon where you are in the work envelope. And you'll see it's not quite, doesn't change that much for the linear versus you have it all over the place for using the rotary drive. Okay, the back drivability. Yeah, planetary gearboxes have really good back drivability. They also have backlash. You put a harmonic in there, and that might change a little bit. The same thing, I'm kind of surprised because ball screw drives, I've held ball screw drive linear, and they back drive very, very easy. Even roller screw drives aren't that bad. So I, I'm like, I don't think there's that much of a difference between the two, or there shouldn't be. I definitely agree on the torque, that the linear drive is going to give you much better torque. Especially throughout the envelope is going to be better, where you're going to have some variability there. The speed, I kind of agree with that. It seems to be the problem we're seeing with the linear drives. They're just not as fast as everyone that's using a rotary drive. So that seems like, yeah, it's going to perform better in the metric. The mass, I can believe it, because remember we held the planetary roller screw, not the whole actuator, just the planetary roller screw. That was pretty heavy, wasn't it? So,
Yeah, yeah, it wasn't heavy.
yeah, yeah, it wasn't light at all. So, yeah, I think it would probably win on the mass. The center of gravity surprises me a little bit. I guess they're saying that they can get those motors up a little bit higher, where with the linear drive, you still have a lot of it hanging down. So you're not able to move the center of mass as high as you want. Because again, the higher up, the better. And then the compactness, it also don't necessarily, I guess it seems it depends on how good you are in your engineering, that I kind of disagree that the linear is going to be so bad when it comes to the compactness. Uh,
In fact, I
yeah,
feel when I saw the two crank
yeah,
moving, it seems, to be honest,
yeah.
a nightmare.
Yeah, yeah. So basically, let me go back to this. This is kind of let me say I got to go back and find where that picture. There we go. Here's their design. Okay. So you'll see this is a little bit different than the AGI bot we had in there, and that it's putting them on different sides makes sense because now the cranks don't interfere. Remember, we had them interfere. That's why, and this tends to be the actuation strategy that just about everyone is using. That AGI bot, I think, was like a very early version. It's kind of open source. I think you can almost 3D print the thing yourself and put it out. But this is a bit more like how Unitree and Agility and others, they do it a bit more like this. They are up very high, close to the knee with these long cranks, and the cranks don't get in each other. And I guess you can get a certain amount of compactness. But here, I don't think they're doing as elegant a job of packing that as Tesla did. So, I could see why they say, "Oh, yeah, this is way more compact than that." And I think it's just like, well, your particular way of designing, I don't think was as good. So a good designer would be able to get that compactness down. So I would not use that as a metric. I would say ignore that unless my design is so bad. Yeah.
Which part of that? Because I understand this is the AGIs, but this is not similar to
No,
Tesla
no, no.
or the
This
same.
is basically a generic. So they were saying, imagine designing your own, and they're just coming up with their own way of being able to design it. So they came up with something like this, and based on their design criteria, and they have different parameters that are like the distance that these balls would be back from the center in order to get adequate torque and range of motion and everything else. And they're using a specific actuator from Wittenstein, which maybe is a bit bulky, or has certain size restrictions and torque restrictions. So there's so many variables in there. And again, you have to look at their paper to understand how they did it and how you might plug your own actuator in there to come in up with your own decision of what would be the best approach. But that's why I say you have to take it with a grain of salt. Every actuator is going to be a little bit different. Every way that you design it's going to be a little bit different. And I think Tesla has shown that you can still make one that's pretty compact. It's just going to come down to the speed, reliability, cost, and everything else. Now,
Let me.
yeah, mhm.
Can I ask a question or
Sure, go
wait?
ahead. Yep.
Yeah. Maybe it's first question when you already saw this. Yeah, different humanoid company. They have a different approach to design their approach, and it seems most of them going for the linear actuation.
Yeah, half and half are doing that for the ankle, and half are using the rotary. So from the outside, it looks like they're doing the same way, but inside they're using rotary. So Unitree, you'll see that mechanism and you'll imagine, go, oh, that must be a linear drive in there because I see those two cranks coming on down, or those two rods coming down, the connecting rods. But the reality is inside they're connected to a Revolut. So they are basically RSU, they're not SPU. But Tesla's not alone there. Like I say, there's at least 4 or 5, maybe 6 other companies that are also doing it with linear actuators because there are some advantages. But that said, the disadvantages seem to be everyone that is using that actuation strategy have yet to see their bot move quickly. None of them are really walking that briskly with it. However, everyone that's using the RSU, they're dancing and running fast and jogging and, and doing backflips and everything else, and which is kind of a surprise because it seems like the linear ones give you better torque, and that better torque might be able means that I can squat down and lift something really heavy, but it may not be able to deliver the velocity that you need to like allow you to jump and do everything else. So basically, that's one way of looking at it. In the end, it's like, what's the bot performance like? There could be a whole bunch of other things coming in, but you got to start somewhere to decide. So if you've decided I'm going to use linear drives, what they're proposing is this is sort of a way to help you optimize your overall design because they're trying to come up with the optimal SPU and the optimal RSU and then compare the two. And you can say, well, I don't care about comparing the two. What I care about is like optimizing the particular SPU design I'm going with because we've already decided that that's the route. for a variety of reasons. So that's where I think is going to be good. The takeaway shouldn't be, oh, abandon linear drives in that. It should be, you've got to make the decision based on a bunch of other factors, which is going to be extremely important. So again, if we kind of go back, the interesting thing is that, they're looking at the operational region for the ankles. And, the original ones, they thought, oh, we got ankles of plus or minus 35, and then they'd be able to do like pitching of 70 to 30, only to find out that in order to make things compact and everything, to without having all sorts of interferences, that goes down dramatically. So the AGI bot, I think, was up around 25. The Tesla's about close to 30. It's really hard to get to 35 in your roll. And even then, the Tesla, if we look at that, it's even more limited than this. No one is able to do anywhere close to 60. Both the AGI bot and the Tesla bot, you don't get that much pitch. You get interferences really pretty quickly there. And so I can sort of show that briefly, just to give you an idea of what I mean. So once again, coming on back here, and we get this. So, looking at this, what I mean is that when you go and pitch, so here is our pitching, you'll see, bam, we already are getting ready to hit right there. I mean, it's very, very, very close. And my pitch is like 35 back that way. And then I'm going to come on up to here, and you can't get much more at this point, they actually are running out of length here. There's only so far you can move that. And the other thing you got to be careful of is that as you're pitching this, you see how this is moving forward. If I pitch that anymore, that actuator is going to move forward and is going to hit the front of the shim. So, that's another thing that limits. So that means I'm getting to minus 25. So the range of motion is 35 to minus 25. That's only about a total of 70. So, you can't get anywhere near 60 because of, but that's fine. If you actually look at your foot and try doing a similar thing, you'd find out you don't have much more flexibility than that anyways. And again, it comes down to the fact that this actuator is rocking around in there. You've got to make room for its movement so it doesn't bump into to different things. And that sort of adds some complexity to your overall design. Whereas this design, you'll see the actuators do stay fixed. You don't have to worry about the actuator body moving, but you do have to make sure there's enough space for the crank and everything else to move around. But you have also sort of a similar issue with this one here, is that its range, I think, on that one is like minus 45. So it's a little bit more as far as bottoming out there. So that's about the bottoming out part. And then up to about there, you can get about 30. But even then, I'm kind of concerned when I was looking in there that other parts of the mechanisms are getting mighty close to each other. And of course, at this part, the things are inside out. So, I mean, realistically, it's like about 20 when it's going down there. So, and then you have the movement this way, which is, I think, also this one here. Yeah, I think it was able to get plus or minus 25, and that's a bit tight. And again, you have to worry about the crank self-intersecting in there. So that's not necessarily a good design. This one, the idea of having them parallel, or rotated 90 degrees and having the cranks on opposite sides, that's much better. You avoid that particular issue.
I want to 3D print these models.
Yeah, yeah, yeah. I think.
Really?
Yeah, yeah,
I
yeah,
want to do
yeah.
that just to play with that. I think it would be nice to have this 3D printed
Yeah, yeah.
and play with
I
them.
can get you
You have a 3D printer.
yeah,
You have the 3D printer, so,
yeah,
so
yeah.
you can print.
And I'm not sure if you can print them in one piece. You might need a bigger printer, but I think there are some
Yeah, but
STL
multiple
files out
pieces.
there that you can
Yeah.
use for sure. And the last thing I just want to mention is the kind of the last point after looking at the range of motion here. Oh, okay. So you'll notice the mechanism in the wrist is the same.
Yes.
It's exactly the same. And they focused on the ankles, and what they should do is the same thing here, because ironically, there are no RSU wrists that I'm aware of. Maybe there's one out there, but most of the wrists that do a parallel actuation mechanism like this are the SPU, or they're serial. So remember, the whole point of this paper was just saying, well, a serial ankle is a bad idea. That you should use one of these two. And I agree, with that for the most part, but it can be done. with serial. So some people may want to look at that, but for the most part, it's going to be one of those two actuation strategies. For the wrist, it's like either serial or this, and no one has gone with RSU. Why? Now there's slightly different requirements as far as range of motion. Rigidity is not as important, or let's say structural isolation. So when you're walking, you're banging on the ground, and one of the advantages of using those two approaches is it helps absorb a lot of the shock. And so the requirements are a little bit different for a hand than it is for a foot. And that's why they have to go through and come up with another methodology. And maybe they're working on that already. And if they're not, and if they actually see this podcast, um, then I would encourage them do the same thing for the wrist as well, and see if there would be particular designs for that. So yeah, that's all I have to say. I don't know
Thank
if
you.
there's any other questions.
No, no, it's very fantastic. I appreciate first of all breaking down this in the cat model, that your conclusion, your own conclusion, and what is exists in the humanoid space now. Because I think one could ask me, I mean, how can I merge the best of the two worlds if I have to have the linear actuation and also the rotary, the two cranks moving? So do you
Hmm.
think there is any way to combine the torque and velocity at the same time?
Yeah. So yeah, is there like a another strategy of the two? It's like either linear or rotational. A lot of times, the reason why everyone is choosing the rotational is just because that's the kind of actuators they want to source. They don't want to deal with linear, so they just we'll go ahead and do it. And it turns out that maybe that's the better strategy over linears. And then there are others that are fine with the hybrid, the idea that we'll mix and match because we really think there's advantages of one to the other. It will remain to be seen because it seems that there has been some difficulty getting good quality linear actuators, or they're very expensive compared to rotary. So that's why you're seeing so many going in kind of that direction. But there's still a few out there. Even Nura, they dropped a lot of their linear actuators, but they kept them down in the ankle and they kept them in the wrist because they saw that there's definitely utility keeping them there, even if they decided, it doesn't make sense in the knee, it doesn't make sense in the elbow, it doesn't make sense in the waist. They basically got rid of it everywhere except in those two key places, probably because they say, yeah, this is a design advantage. And they could have gone rotary in the ankle and still kept the similar kind of mechanism. They could have just gone from SPU to RSU, and that would have been very easy considering how much they changed everything else. But, their analysis anyway says this is a better strategy. So, yeah, in many cases, everyone's trying to minimize the part count as far as like the number of actuators they need. And that's understandable when you're designing your own actuators and you really believe they have to be, optimal for it. But there's so many actuator companies out there now. It's like you could almost have the optimal size actuator for each joint. You could go through and say, what's the best size one? Probably go in a catalog and find one now, or you're getting really, really close to that. So in that case, I don't think there's any disadvantages to looking at the idea of having different sizes. Because again, Nura had to do that because and Tesla as well, the linear drives in the ankle and in the wrist are different sizes. They're not the same ones. So you're having to source two different sizes there because it makes sense. You need more strength out of the ankle.
I really appreciate that. And the conclusion of the paper, you disagree with that, I think, even if that analysis, because I think maybe if we think maybe a better way to do this calculations in a
Again,
thorough way,
there's there's just so many variables. Like, that's why I just wanted to point out is like, wait a minute, that was ball screws versus ball screws versus planetary, and maybe it should have been planetary roller screws versus harmonic drives. So there's a whole field out there, and they were just saying that these are the ones we've chose, and we've tried to optimize our design around those two, which we think are about the same. And this is our conclusion. And like I say, I think that some of the points are agreed, and some of them I think they could be a little, or the weighting functions you put on some of it, like back drivability. While it's nice, I don't think necessarily having better back drivability is an advantage. It's just that if one of them is not back drivable versus one that is, and that's different. And a lot of people will say you want it because you want to have something which is kind of QDD to make it a little bit easier for force feedback and everything else. That you kind of want that compliance for the control. But so long as it has enough, I don't think you have to worry too much about it. I would worry about things like speed, maybe a little bit about torque, and then the manipulability. They both are about the same, so they score about even there. And the center of gravity, I mean, that was kind of interesting that it wasn't, but again, I think it comes down to the design. Yeah, it's nice to get it up as high as possible, and those things are just gonna weigh more. At least I certainly the planetary roller screw is pretty dense, but maybe they'll be able to come up with lighter ones in the future.
Okay. And you also commented about the 1X video. I would love if you can share
Yeah,
what he
yeah.
noticed.
Yeah.
Yeah.
I let's see, we have to find it, but, I think it was in the early morning hours of Friday. Um, um, I Show Speed, which is a pretty popular influencer on YouTube, had, like an hour to visit at the 1X headquarters in Palo Alto. We went in and met, Neo. There were some hijinkses and stuff like that, but the main thing was, he got a chance to use the teleoperation control. And so I made sort of some comments about how the teleoperation is working. And we have a long, I mean, really a long video. I think it was like 2 hours long back in January where I showed the setup that I have here for being able to do teleoperation, what I've learned, what I learned 10 years ago, and what some of the challenges are. And a lot of it is having sufficient tracking data on your body. And if you don't have enough, it's really hard to get the bot to faithfully mirror what you're doing. So a lot of setups, it's like, well, I just have the head and I just have the hand. And that's not enough information because you have this redundancy in your elbow. You know, what's your elbow doing? Trying to figure out what that is. It also turns out there's like redundancy in your body. So if your head turns, is your head turning or is your body turning or is your torso turning? Trying to understand those things. And usually that means more sensors, suiting yourself up and doing everything else. Well, they managed to actually, well, not so much they managed, but Meta managed with the Meta Quest 3. They have these cameras that are built into the headset. So when it's on there, it's tracking your finger gestures and your upper body and everything really well. So they were able to tap into that information to inform their inverse kinematics to make sure that it actually moves the way the operator is. And that was a really cool thing to see because those kits are like under 500 bucks. So that means, wow, this is actually scalable because the problem is the scalability is like before you scale, you need to have good teleoperation because if you get crappy teleoperation, that's garbage in, garbage out. You're not really collecting good data out in the field. So you've got to make sure you have something. And if you get something that costs tens of thousands of dollars to get the fidelity that you need, that's not scalable. But if you can just have someone go down to Best Buy and buy one of these things and like they've got everything they need because it's working well, that's a step change. So that's not so much that they've moved the needle. It looks like Meta has potentially moved the needle by having something which is really pretty good. So it was interesting to see how the operations were. And then there are definitely some built-in safety. So there's two things that we sort of happened is that the arm uh, speed was taking his arm and kind of moving it down. He also was doing some other things. You'll notice he was shrugging his shoulder. Okay, that's a degree of freedom the bots don't have. So even if the MetaQuest is saying, "Hey, he's shrugging his shoulders," like there was absolutely nothing that Neo could do. But the main thing is the elbows were always kind of following it right, and there was this kind of this motion that he did a few times like that, where the arm was coming up and getting closer and closer to the singularity. Like once it was like about there, and then it was there, and then suddenly Neo locked, and I wasn't quite sure what that was all about and I assume it's like it looks like it was a singularity that it probably got in the singularity and stopped like that. But the other possibility was he may have accidentally triggered an e-stop, because when you're doing this and you get the hand controller and stuff like that, that's a very easy thing to do. So it could have been one of those things, but 1X basically confirmed it's like, yeah, that basically was a safety thing because there was a velocity error. Now, there's a couple of ways a velocity error could be handled. Is that I contended and said, well, wait a minute. It's like the velocity error probably happened because you were near the singularity. So from the singularity episode, we sort of talked about this idea of an event horizon and that a whirlpool definitely creates a lot of waves and it's still turbulent water even away from where you think it is. So even if you're not at the singularity, if you're anywhere near that, you are swimming in turbulent waters and you're going to have a hard time. So it's possible they kind of get close enough because it was inching up and up and up, and then it kind of stopped and went down. Bernd said that while it was a velocity error, it had nothing to do with it. Actually had to do with the end effector. So basically, he was saying the hand was moving too fast. It's like there was enough velocity in there to do it. I'm sure it was like higher than it should have been normally, but it really was that. And okay, so why would you do that? Why would you limit the hand velocity if you have more than enough headroom to do that? And the reality is because it's like you don't want to break glass. Okay. So imagine, you know, Neo is in front of a glass window, but I'm not. I'm like over here. I don't see what's going on. And I'm dancing around and I go like that really quickly with my hand. It will go right through the glass. So the idea is like they're limiting the speed to make sure there's no impact, that you don't hit someone, that you don't break something else. So that's where they're dropping it down. The other example that they showed is Speed decided to do a backflip with his headset on, and this was uh, at 1X's headquarters. So he's doing it in a venue he's never been in, on a concrete floor, wearing a headset, and he does this backflip. And it's like, wow, okay, if you want to just be able to do that. And Neo, he was moving around, and Neo was following him. And then as soon as the backflip happened, Neo just stopped. Which is like was the right thing for Neo to do. It's like you should not have attempted that, and a lot of it just came down to, again, it was like an overspeed error. It's just like, "Whoa, this is something that is actually dangerous. I will not do it." So, I think that's a good thing. I hope more companies follow kind of that way for safety because we've seen a lot of other bots that seem to not be as safe around people and doing kind of some silly things. So, that was encouraging to see that there are limits on things like that. So yeah, that's pretty much ruined. So if you want to understand a little bit more about this time, we have 2 episodes and they're long, and they were back in the spring. One on the singularity and one on teleoperation.
I will link them. Again, Scott, that was really fantastic, and I really enjoyed it. This analysis. What we should name the episode? I think how to design the knee. What would be good
Oh boy, I
title
had to
for
come up with some, obviously something about ankles.
something waist not
Mm.
something like the old
So
episode.
there must be some expression with ankle. I mean, the only thing I can think of is like ankle
Yeah.
biters, you know. uh,
So we think about it.
yeah, we'll come up with something.
Yeah. Okay. So I'll stop us here.
All right. So